Okay, so let's welcome you to the second speaker of this morning session. So it's a pleasure to introduce one of my colleagues at the Chinese University of Hong Kong, Shenzhen, Arnulf Jentzen, who's also based at the University of Münster in Germany. Arnulf, he did his PhD at Goethe, sorry for the pronunciation, and postdoc at Princeton with Wien and E, followed by an assistant professor position, ETH. He's held and has been awarded many prizes, including the Felix Klein Prize. He's going to be speaking on overcoming the curse of dimensionality from nonlinear Monte Carlo to the training of neural networks. Arnulf, please take it away, and thank you very much for agreeing to speak here.
Yeah, thank you, AJ. Yeah, I'm there. Thank you, AJ, for the introduction, and also many thanks to you and Raul and all the other organizers involved for giving me the opportunity to speak here. And to participate at this workshop about stochastic numerics and statistical learning. Yeah, and in this talk, I particularly want to highlight a few strong connections between stochastic numerics, stochastic algorithms, particularly Monte Carlo algorithms and machine learning. And so in the first talk, which is with the first part, I want to present one result about approximating nonlinear PDEs by deep neural networks. And the arguments, the proof of that result, so that result shows that basically that deep neural networks can provably overcome the curse of dimensionality in the approximation of semilinear PDEs. And in the proof of that result is strongly based on stochastic algorithms, on stochastic numerics, namely suitable nonlinear Monte Carlo algorithms. And then I want to go to an algorithm inspired by this theoretical result, and thereafter some results about the analysis in the training of neural network of stochastic gradient descent optimization methods. Okay, so let me start now with that, showing that deep neural networks can provably overcome the curse of dimensionality in the approximation of semilinear PDEs. And though to sketch what is a deep neural network, okay, one in the most simplest form you can think of it, probably many of you know it already, but in the most simplest form you can think of it as a function which consists of multiple compositions of affine functions and certain fixed nonlinear functions. Okay, we have an affine function here in this example here from the R5 to the R6, and then we have a nonlinear function from the R6 to the R6, the fixed nonlinear function, and then we have again an affine function which changes the dimension this time from the R6 to the R7. Then we have to the R7. Then we have again a nonlinear function from the R7 to the R7, and finally one more, an affine function from the R7 to the R3. And very loosely speaking, the way here to these multiple compositions, how the information is processed, that way is inspired by natural neural networks, by how they appear in humans or animals, and in taking that inspiration into account, this kind of schemes, this kind of classes of functions are referred to as artificial neural networks due to that inspiration. Okay, so now let us formalize that. That was just a sketch, a figure to give a first impression. Now let us precisely, rigorously describe artificial neural networks, and then using that terminology, formulate a statement that such objects do overcome the curse of dimensionality in the numerical approximation of nonlinear PDEs. Okay, so let's first formulate the nonlinearities. So before here in this slide, we have a nonlinearity from the R6 to the R6, and then another nonlinearity from the R7 to the R7, which are fixed. And they are usually component-wise applications of a fixed nonlinear function. And maybe one popular, or maybe the most popular choice is this class of functions. So for every dimension L here, for every natural number L, and for every vector in the RL, we have this nonlinearity that A of x is equal to the maximum of the first component and 0, the maximum of the second component of the vector and 0, and so on, and the maximum of the last, the else component and 0. And in this specific choice of function, okay, with the one-dimensional version, looks like this. Okay, that's called this ReLU activation, rectified linear unit activation. Okay, yeah, but it could also there are also smooth variants of it. For example, here's a soft plus activation, which looks like a smooth version of this function. Yeah, or also others like leaky ReLU activation. And the theorem which comes now does not depend on the particular choice of this ReLU activation. It would exactly in the same format be true if you replace this function here by the soft plus activation, the smooth soft plus activation, or leaky ReLU activation. Okay, now we have these nonlinearities. Now, in between the nonlinearities, we need the composition of these affine functions. And affine functions, how can then they be described? They are described through a multiplication with a matrix and adding a vector. That's an affine function. Okay, so from the RK to the RL. And so we have, so to describe each of these affine functions, we have a pair of a matrix and a vector. And now we build a large set of all such matrices and of all such pairs of matrices and vectors. And this is the set which here is denoted by a fat N, a boldface N, okay, for neural networks, and is here nothing else. So you see here, this is the Cartesian product. So that's a pairing of here matrices, Ln times Ln minus one dimensional matrices, and Ln dimensional vectors. And so that's, this Cartesian product here is a set of pairings of matrices and vectors. And now we want not only one such matrix pair, but we want a whole L tuple of such matrix per pair. So we have here again another Cartesian product from running from N from 1 to L of all such matrix vector pairs. So this object here builds a set of all L tuples of matrix vector pairs. And now we have a union over all natural numbers, and union here over all natural numbers L, and here union over all natural numbers L0, L1, LL, to describe all possible dimensions. And yeah, this is here the set of all artificial neural networks, and roughly speaking, so it's just a set of all tuples of arbitrary length, with each component of the tuple being a matrix and a vector, being a pairing of a matrix and a vector with appropriate dimensions, so that you can compose them. Okay, and now for taking this set into account, we now want to define for each element of the set, we want to assign a function. Okay, and that's done in the following procedure. So for every natural number L, the length of the network, and for every dimensions of these hidden layers in the network, L0, L1, LA, and for every L tuple of pairings of matrices and vectors, now describing a neural network, an artificial neural network. So that here is a subset of this set boldface N. So this U is an element of this set of neural networks. We assign now a function, and that function here is denoted by R, because realization function RU, which maps from the R to the power of L0 to the RLL. And we also assign the number of parameters. So we want to count how many scalars, how many one-dimensional real numbers do we need to describe these networks, because that corresponds, roughly, loosely speaking, to the amount of memory you need on a computer to store these objects. For example, if you think of double precision, so meaning you store each real number, you approximately store each real number with 64 bits, with 8 bytes, then it means that this PU, this number of parameter, multiplied by 8 bytes, this is the amount of bytes that you need to store to approximately store the network. Okay, so more precisely, So we define for every L and L0, L1, LL layer dimensions and U such a network, such an L tuple, we define this function RU from the RL0 to the ILL, and this natural number PU through the following procedure: for every vector x0 in the IL0, x1 in the IL1, x2 in the IL2, and so on, and xl in the ILL, with the recursion that xn is given recursively as this nonlinearity here applied to wn xn minus 1 plus bn. So these wn and bn, they are just the wn is a matrix in the nth component of this L tuple U, and bn here is a vector. It's a second component in the nth component of this L tuple U. Okay, and then so with that recursion, we define that RU of x0 is WL XL minus 1 plus BL, and PU is just the sum, for how many real numbers are in this matrix, how many real numbers are in this vector, and so on, and how many real numbers are in this matrix, and how many real numbers are in this vector. And if you sum them all up, you have L1 multiplied by L2 multiplied by L0 plus for the first matrix plus L1 many for the first vector, and so on. You have this L times, so you have the sum from K1 to LK multiplied by LK minus 1 plus 1. Okay, so this is the number of scalars, real numbers used to describe the neural network U here, big U. Okay, and now this is a common terminology in the literature to describe artificial neural networks. And with that terminology in mind, we can now formulate the theorem, namely that such objects, such classes of functions, can approximate PDEs, semilinear PDEs, semilinear heat PDEs without the curse of dimensionality. Okay, so let's make the statement precise. So let T and kappa be two real numbers bigger than 0. So we consider an evolution equation, and the time horizon of our PDE is the interval from 0 to T. And then we also need to impose some growth conditions on the solution of the PDE itself. Roughly speaking, I mean, if the solutions of the PDEs, they grow in the dimension like double exponentially quick, if they grow very quick in that dimension, then it seems to be hopeless to have the opportunity to approximate them without the curse of dimensionality. Okay, so with just a polynomial growing dimension. So that's why we use this assumption kappa, this real number kappa here to avoid such a quick growth. And then we have also a nonlinearity in the PDE, which is here just as it's common denoted by a real number by f, which is here nonlinear Lipschitz for simplicity in this theorem assumed to be Lipschitz continuous. Okay, but then in follow-up works, it has been generalized to non-Lipschitz and also more complicated nonlinearities. And then, okay, we want to make a statement about the curse of dimensionality. So we want to make a statement about how the complexity grows in the dimension of the PDE. Then if we want to make such a statement, we cannot just fix a 10-dimensional PDE or a 7-dimensional PDE and then study the error, the discretization of that fixed PDE, but instead we need to vary the dimension. We need to consider a whole sequence of PDEs, or family of PDEs indexed over the dimension. And for each of these sequence of PDEs, for each of these PDEs, we have a corresponding initial value, which is here denoted by GD. So that's the corresponding initial value, which is here for simplicity assumed to be continuously differentiable. And then we have the corresponding solution of the PDE here denoted by UD, which satisfies this semilinear heat PDE. And here, just for simplicity, this operator is just the plain vanilla Laplace operator. So it's just a semilinear heat PDE, but this operator could also be replaced by a general, possibly degenerate second order differential operator, second order Kolmogorov differential operator, and possibly degenerate. And here this nonlinearity, maybe non-Lipschitz, may also depend on the gradient, but then this operator cannot be degenerate. Okay, so then we also need to impose some condition on the initial condition or on the whole solution, namely that this here assumes that the initial condition and its derivative grow at most polynomially, like this constant kappa here, in the dimension of the PDE and in the spatial variable. Okay, and when you have such a bound for the initial condition, then one can conclude that also the solutions itself satisfy a similar bound. So then that's what we want to avoid, that the solutions grow exponentially in the dimension or the spatial variable, because then it seems to be hopeless. If the function is growing so quickly, so huge, then it seems to be hopeless to be able to approximate it with the amount of memory being only polynomial in the dimension. Okay, and now we also need, so if you think of this being a second order differential operator, so it could vanish, so it should be just zero, and the nonlinearity may also be zero. So if this is all zero, then the solution for all times stays just the initial condition. And then in general, there are counterexamples. You can specify function, C infinity function, which cannot be approximated without the curse of dimensionality by deep neural networks. So in general, you cannot expect that the solution can be approximated. But the point is, if the initial condition of your problem, if you have a physical problem where you have data, you have given initial condition, or a finance problem where you have a portfolio optimization, you have a given specific, explicitly given initial condition where you can easily verify that it can be approximated without the curse of dimensionality. Okay, it's quite difficult to write down something which cannot be approximated without the curse of dimensionality, which also doesn't grow so quick. Then the conclusion is that then the whole solution can be approximated without a curse of dimensionality. And so let's formalize this assumption that the initial condition can be approximated without the curse of dimensionality. So for every dimension D, for every precision epsilon, there exists a neural network G, so that the difference between the initial condition and the realization of the network is smaller or equal than epsilon multiplied by kappa d to the power of kappa 1 plus the norm of x to the power of kappa. So if you consider this right-hand side here of this bound between the difference between the initial condition and the neural network, which is assumed to exist, and now if you push this epsilon here on the right-hand side to 0, then you see this right-hand side converges to 0. So as arbitrarily small as you choose the epsilon, maybe choose epsilon is equal to 1 over 10,000, then you know by this assumption there must exist a network which is somehow close with a precision 1 over 10,000, roughly speaking, to this initial condition. Okay, so the initial condition can be approximated by neural networks, and the amount of memory that you need for these networks may only also grow like polynomial in the number of parameters of the network, in the dimension of the PDE and the inverse of the precision. Okay, and then so yeah, for example, you can think of examples where GD of X is nothing else but the maximum of all components, or maybe something like maximum X1 minus K and 0, and then some sum here, and J's who have something like a financial option or something, classes of this. For such functions, you can all verify that they satisfy this assumption. And then the conclusion is that if you know this for the initial condition, then there must exist also a real number C bigger than 0, which does not depend on the PDE dimension and the approximation precision, so that for any dimension of the PDE and any precision, there must exist a network such that the distance, the L1 distance between the solution of the PDE and the realization of this network is smaller than this epsilon, and such that the amount of memory, the number of parameters you need to store this network, grows at most like a polynomial in the dimension, and like a polynomial in the inverse of the precision. Okay, so the spirit of this theorem a few more comments. So one comment is that for these neural networks, it's really essential that they are deep. So even if these initially can be approximated by shallow neural network, here it's essential that these are deep neural networks whose deepness grows, whose this number of affine transformations, this L here, grows with the dimension and the inverse of the precision. And roughly speaking, the intuition behind the theorem, of course, there are also classes of functions which can be approximated without the curse of dimensionality by shallow neural networks, but maybe not by deep neural networks, or which can be approximated by finite differences without the curse of dimensionality, but not by deep neural networks if you use the same number of parameters. But the philosophy of this theorem is somehow that if you restrict yourself to the class of function to solutions of semilinear PDEs, then for this kind of structure, deep neural networks seem to fit very well, and because they can provably approximate such class without the curse of dimensionality. And of course, semilinear PDEs, with their motivation from physical problems, they describe the reality. So that's so it seems that deep neural networks are quite appropriate, quite good class of functions for approximating such high dimensional objects. Okay, and as I said, there are many ways where this work has been generalized, like for gradient dependent nonlinearities or much more general operators. And so the key argument in the proof is actually that there is another Monte Carlo algorithm, a nonlinear variant of the standard Monte Carlo algorithm. And that nonlinear Monte Carlo algorithm, which we refer to as multi-level Picard approximation, can probably approximate such PDEs without the curse of dimensionality. And it's the only algorithm until today for which one can prove that which probably approximates such PDEs without the curse of dimensionality. So maybe there exists another Monte Carlo algorithm, another algorithm which can do that, but until today, nothing has been proven for this general class, for general semilinear PDEs. And then the argument in the proof is just that one takes this Monte Carlo algorithm and approximate the Monte Carlo algorithm by deep neural networks, and thereby obtains the conclusion of this theorem. Okay, so few more comments is also, in this theorem, so it's just about the existence, doesn't tell how to get actually the neural network that approximates the solution. But when you think about the proof with the Monte Carlo algorithm, then you have also a procedure how you can coin this neural network, not by training with stochastic gradient descent, as it's usually done, but by following this algorithm, how to approximately compute such a neural network. Okay, so then what other comments is that, so the deepness is really essential, and there are also counterexamples of certain functions which are smooth and bounded, but which you cannot approximate by shallow neural networks, where you really need the deepness, and this you can find in this reference here. For example, you can think of these functions to be sine and then the product of all components. These are C-infinity functions which can be approximated by deep neural networks without the curse of dimensionality, but you must have exponentially growing memory if you want to approximate them with shallow neural networks. Okay, and now from this theorem also there's related some classes of algorithms where one works as follows. So one wants to approximate a certain class of PDEs or certain computational problems, and suppose you have already an algorithm for such class, a class of Monte Carlo algorithms, but you want to approximate that, solve that problem not only once, but again and again. So it's a parametric problem. And then this procedure of this algorithm, which somehow inspired by this kind of theorems, is that you first throw your Monte Carlo algorithm, but with not so many samples, a bit less accuracy, and then you replace all the random variables which you have thrown by trainable parameters, and search by means of stochastic gradient descent or other similar optimization procedures for better random variables, in the optimization landscape, which will replace the originally random variables with which you have chosen. So on that way of that training procedure, somehow you can think of, you also see quasi random numbers. And this is this work where we did this kind of tested this kind of algorithm. And here's one numerical example where this tested in the simple example of the Black-Scholes model, maybe the most simplest and most popular financial derivative pricing model. Okay, so where we want to solve this Black-Scholes PDE, which has this Black-Scholes model 5 parameters, namely the time of maturity of the option of the considered financial derivative of the call option, and then this is a initial stock price of the underlying stock, so initial price of the underlying stock, and this is the strike price of the option, and then this is the interest rate, the risk-free interest rate in the model, and this is the volatility of the stock in the model. And now we want to approximate this, solve this Black-Scholes model not only for one choice of parameters, but on a whole region, and a whole 5-dimensional set. And then one can try to employ neural network, for example, with 2 or 3 hidden layers, and then try to fit this Black-Scholes PDE solution. Then you see here the errors in the L infinity sense. And one can also use Monte Carlo, where you have 0 training time. You just have a Monte Carlo or quasi Monte Carlo, which is even more accurate with 0 training time. Or you just choose Monte Carlo, but with a lower number of samples, and then try to find better random variables for that specific problem. So these quasi Monte Carlo random variables, they are universal for all kinds of problems, not problem specific. And here somehow this is inspired in some way through quasi Monte Carlo, this learning the random variables, where the random variables are then trained based on the specific problem, namely exploit the structure of the Black-Scholes PDE situation here. Okay, and there you can see that the error can be achieved to be quite small, even so the number of trainable parameters is lower than the samples here for quasi Monte Carlo, for instance. Okay, so with taking that into account, I want to go a bit more now to the analysis of the training procedure, okay, of this stochastic gradient descent here underlying of this training procedure. And maybe the most simplest question that one can ask when training with gradient descent is actually, or stochastic gradient descent, whether there exist minimizers in the optimization landscape. And that the question whether there exist such minimizers, whether the function actually has a minimizer or whether the minimizer is taken at infinity, that strongly depends on your neural network architecture actually, and strongly depends on your activation function. And this is now, for simplicity, restricted here to this simple class of neural networks with just a one-dimensional input and just one hidden layer and a one-dimensional output. And in that simple scenario, it can be answered positively for the ReLU activation, but negatively for many smooth other activation, like the soft plus activation or standard logistic function. So more precisely, we have the following statement. So here, let L be the number of neurons on the hidden layer, and let P here be again the number of parameters as before from the network, which is here in this example just 3L plus 1, because I mean before this PU was equal to the sum from K1 to L, LK multiplied with LK minus 1 plus 1. And now here in this example, we have just L0 is 1, and L1 is this L here, and L2 is again 1. So then in this case, in big L is equal to 2. We have just 2 affine transformation and 1 hidden layer. So then we have here just L1 multiplied by L0 plus 1 plus L2 multiplied by L1 plus 1. But this is nothing else now here. This is L. So we have L multiplied by here 1, so 1 plus 1 plus here again 1, so we have here 1 multiplied by L plus 1, so this all here is 2L plus L plus 1, so it's overall 3L plus 1. Okay, so this is the number of parameters here, just this, in the case of this simple architecture here. And then, okay, we have an interval A and B, two real numbers, on which we want to approximate the function of interest, which is here, this function we want to approximate is here this f from the interval A, B to the reals, which is assumed to be a continuous function, so quite general condition. If you think of, here's just one dimensional, but in applications, you can think of this being a solution of a PDE, which is, of course, in most scenarios continuous, or you can think of this one as being a function that assigns to each picture the probability that there is a cat on the picture, yes or no. I mean, in the application, you have just 0 or 1 at the end, because you say if the probability is bigger than 50%, then it's greater or equal to 50%, then it's there is a cat on the picture, and if there's smaller than 50%, then there's no. But the probability that there is a cat, that in real life models, that should be a continuous function, I guess. And then, okay, we have the underlying measure for the probability distribution of the input data. So that's typically a probability measure, but here can be a measure mu. And but you can think of it just of a probability measure. And then the function we want to minimize here, this risk function from the parameter space to the reals, is just nothing else but R of theta. So now it's just our network with one hidden layer, and then one can explicitly write down the realization without this lengthy recursion. More formally, so we have here these network parameters theta L plus J and theta J x. So that's here an affine transformation. We take this x here from the interval AB and multiply it with the theta vector and add another, multiply it with the theta real number and add another theta real number. So that's an affine transformation. Then we apply the nonlinear activation function, which is here again maximum of x and 0. So this function here. And then we apply another affine transformation. And then we subtract that from the function that we want to approximate. And so that's the common standard mean square risk function. And yeah, then the question is of that theorem is whether there actually exist minimizers in the optimization landscape, and that can be answered positively. So there exists a vector theta in the RP such that this R of theta is equal to the infimum over all possible network parameters. Okay, and it looks like a quite trivial statement, but it's actually not so easy. It's also still an open question if you go to deep neural networks. It has been generalized to different architectures, but shallow, like residual neural networks, and also multidimensional, fully connected neural networks in these two works. But it's still an open question in the case of deep neural networks. And it has also been disproven if you replace this nonlinearity here, say example by the soft plus activation. So if you take a smooth variant of this plus function, okay, so the nonlinearity looks like the Relo activation looks like this. This is the Relo activation. Now, if you take a smooth variant of that Relo activation, this says a soft plus activation, or here in this in this nonlinearity, or the standard logistic, another smooth variant activation, then for such smooth activation function, you can disprove the statement. For the leaky Relo, you can in turn prove it. Okay, there exist minimizers, but for such smooth activation, you can disprove it. And one has to be a bit careful that this question of the existence of minimizer seems to be a bit relevant, because if there exists no minimizer, then you can somehow prove that the gradient descent or the gradient flow trajectories diverge to infinity if you're trying to minimize the function. Okay, okay. So let me go a bit deeper into that optimization question. So this is just about the existence about global minimizers, but usually what happens when you do a numerical simulation? So let's take at the following figure. Then here you have the different risk levels for this different SGD training procedures. Okay, when you take other optimizers like Adam, it looks similar. So here's different risk levels for different independent SGD training procedures. And here, so this gray, so this in this histogram, the gray plot in this histogram comes from the training of with SGD of a neural network with 5 neurons on the hidden layer. Okay, so it's just 1 neuron on the input layer and then 5 neurons on the hidden layer, and 1 neuron on the output layer. And then, so this is this gray curve here. And then in the histogram, and then you can ask, this orange one comes from with 20 neurons on the hidden layer, and this green one here with 150 neurons on the hidden layer. And you see, this is the risk level is the value of the function that you want to minimize. So roughly speaking, when you look at this gray curve here, then you can maybe guess that the global minimizer, now it's overplotted with us, maybe this gray histogram will continue like this, maybe here will be the global minimizer, the value of the optimal value of the risk function in the case where these 5 neurons here are, where L on the previous slide is equal to 5, okay, so where there are 5 neurons on the hidden layer. And then you can see maybe here's only a very, very small probability you end up when you independently throw in this histogram here one trajectory of the SGD training procedure, then maybe only with say 1% or maybe 0.1% you will end up in the global minimizer. In all these other cases, you end up in a good non-optimal local minimizer or a good non-optimal critical point, okay? So that's where you typically end up with high probability. But still, the existence of local minimizers in the optimization landscape seems to be strongly connected to the existence of global minimizers in the optimization landscape. So that's why it still seems to be quite relevant to study the existence of minimizers in the optimization landscape. Even so, one can disprove, not only from this picture here, one can see that the probability to end up in the global minimizer is quite small, but one can also disprove this for Adam and many other optimizers that with the probability to end up in the global minimizer converges exponentially quick, converges rapidly to 0, okay? So we know already that we don't end up in a global minimizer, but now in a very simple scenario, like again, with this 1 neuron on the input layer and 1 neuron on the output layer, and just 1 hidden layer, and also where you further restrict yourself and just train the biases, instead of all parameters, you just train the biases, then you still have many non-optimal local minimizers in the optimization landscape. But then you can really rigorously prove that in the training procedure, you end up in a good non-optimal critical point with high probability not in the optimal critical point, not in the global minimizer, but with high probability in a good non-optimal. What does good mean? Good means that the distance to the global minimizer is polynomially small in the number of neurons on the hidden layer. So converges rapidly, the distance converges rapidly to 0 in the size of the neurons on the hidden layer. And this is the last statement of this talk, what I wanted to present. Yeah, it's as I said, in a very special scenario where you have just the 1 neuron on the input layer, 1 neuron on the output layer, just 1 hidden layer, and also where you just train the biases and not all parameters. And in addition, where also the function you want to approximate is also assumed to be monotone increasing. So it's even more simpler, but still, it's a quite highly non-convex optimization problem with many non-optimal minimizes. And in that scenario, you can really provide a full error analysis, full convergence of the risk function as both. You need the training time of your SGD going to infinity and the architecture of the network going to also to infinity, the width of the network. So it's like discretizing a PDE. You have temporal discretization, the number of corresponding maybe to the number of SGD training steps. And then you have also spatial discretization maybe corresponding to the width of your network. And both need to go to infinity so that you have converged. So let me formalize that now in a bit technical theorem in this very special example, but there you can really provide a full error analysis for the training of neural network. Okay, so let's consider an interval AB again, where you want to approximate your target function. And here the target function is also assumed to be piecewise polynomial. So we later generalize this a bit about piecewise polynomial. And also the P corresponds here to the density of your distribution, of your probability distribution of the input data. And this is F is a target function, which is here to be increasing, assumed to be increasing. And then we have an underlying probability space, omega Fp. Then we have again here this number of network parameters, which is again 3L plus 1 here. And then we want to minimize this function RL from the R to the power of 3L to the reals, which is just this standard mean square distance between the target function and here the neural network approximation. And here we choose as the activation function the clipping activation function that made it a bit easier for the analysis. Okay, so this clipping activation function is globally bounded and looks like this. And then now we introduce for introducing the gradient flow dynamics, we introduce the gradient of that function, but we only train the biases. Okay, so this function G here corresponds to the gradient of this, but only for the bias parameters. So more precisely, so every component of this GL function here is nothing else but the case component is nothing else but the case partial derivative of this RL function here when K is not when K is a bias parameter, otherwise it's set to be 0. And then this theta L here is the corresponding gradient flow process, which just follows with probability 1 the negative gradient flow, as is like in common for such SGD training procedures. And then for the initialization, all components here at 0 are assumed to be independent, and also there are 2 parameters so that we have some half normal distribution at initial time. And then the conclusion is that then there exist 2 real numbers, C and kappa, and random variable CL, so that for every L, the probability that for any t bigger than 0, that this RLT, so that's the function we want to minimize, and that is the gradient flow trajectory, that this is smaller or equal than C multiplied by L minus kappa plus CL 1 over T, that this probability is greater or equal than 1 minus CL to the power of minus K. So you see here, if the number of neurons on the hidden layer, this L here, converges to infinity, then this L to the power of minus kappa converges to 0. And if this T, the training time, converges to 0, infinity, then this 1 over T, CL 1 over T converges to 0. And only if both of them, L and T, converge to infinity, one gets that this quantity here converges to 0 with high probability. Okay, so that's the spirit of a full error analysis for the training with neural networks here in a, as I said, highly simplified situation, just training the biases, monotone target function. But at least in this scenario, one has a full error analysis like in the classical numerical analysis or stochastic numerics. Yeah, and with this last comment, I would like to close the talk and thank you for your attention.
Thank you so much, Arnulf, for this very interesting talk. Do we have any questions from the audience at all? Okay, can we ask?
Thank you for the talk. Just out of curiosity, so for the first result, you had this kappa parameter, which basically was some growth condition, and it didn't appear at the end result. So basically, the approximation doesn't depend on the kappa at all. Is this correct?
Let me show this statement. 1 second. Yeah, so here, I mean, this kappa, the value, I mean, there exists a C, right, in that statement, right? So that C is a function of kappa, right? So let K kappa. So the kappa, you can also refine this exponent here. So for these exponents, you don't need the kappa, but for this one, you need the kappa. Okay. I mean, it depends here. For if you put here some other variables for these exponents, some say kappa 1, kappa 0, kappa 1, kappa 2, then this only depends on kappa 0 and here as well.
Okay, thank you. Thank you very much.
Do we have any further questions? Okay, so it looks like we don't have any more questions. Let's thank Arnulf again. Thank you so much for your talk.
Thank you. Bye-bye.
Thank you. Bye-bye. Thanks. So that concludes the morning session. So we'll resume at 2:30 with Abdul Latif, and the chair is going to be Joachim Big. Thank you.